All right, simple telescope and optics, part 2. So we have an object out here, which is our arrow. We have a focal point, and here's our convex lens. So we know from the definition of focal point that if a light ray here is coming in parallel to the axis, when it hits the lens, it's going to get bent right through the focal point. That's the definition of the focal point. Parallel light rays get bent to the focal point. Okay? And remember, our lens doesn't care. We can do this in reverse. So if I have one coming through the focal point like this, when it hits the lens here, it's going to come out parallel. Okay? Or you can think of this backwards. The parallel light ray comes in, hits the lens, and it goes through the focal point. And there's a third light ray, where a light ray right through the center of the lens is going to be unchanged. And if you've done this right, all three of these light rays, this is something called ray tracing, will hit and intersect at the same point. They all came from the top of the arrow. They all went through the lens, and then they got focused to here. And we have an arrow here. This is our image. And what you can do, if you have a simple piece of white paper, I'm not sure this is going to show up on the camera very good, but you can see we have these lights above us here. I can focus it, and I can make an image of the light on the piece of paper. And it's a real image. It's that image is out in space. I just have to put a projection there, which is this piece of paper, and I can see the image of the light. Okay? That's what we call a real image. It actually exists in space. Okay? This is how you, back in the old days, we used to use slides in our class. You know, the little things with a negative inside of it. Actually, it wasn't a negative, it was a positive, but it was a slide. When you put it in your slide projector, you actually had to put it in upside down and reversed. That's because the lens that they've shined the light through projects it, flips it upside down again. So you have to have it upside down so that when it projects on the wall, it's right side up. Same thing with movie projectors back in the day. Nowadays, everybody uses digital projectors, and that changes things. All right, so that was case 1. Now we're going to do case 2. Case 2, so I'm going to get rid of these light rays. I'm going to leave the same lens, because we didn't change the lens. Same lens, same focal points. All I've done is now I'm going to move my object to in here. All right, so case 1, the object was outside of the focal point. So the object was out here beyond the focal point. Case 2, the object is between the focal point and the lens. So I've just moved the position of the object. Now we have the same exact thing. The lens is never going to do anything different. It's always going to bend light exactly the same way. It doesn't know any different. So a light ray coming in parallel is going to go out through the focal point, just like normal. Okay. Now one coming from the focal point on the same side, I'm still erasing the ones from last time. So a light ray that's coming from here is going to come up here, and it's going to come out parallel. Makes sense? Didn't do anything different. This is the one you can think of it backwards. The parallel light ray comes in, hits the lens, and goes through the focal point. We just make it so it happens to go right through the top of the arrow. And then we have our third one, which is the one right through the center of the lens, and it just goes in a straight line forever. Okay? It's unchanged through the center of the lens. Now, you say, look, these light rays are diverging. They're not going to come together anywhere, not produce an image. But if I project them backwards, so I'm going to extend that one backwards, I'm going to extend this one backwards here, I'm going to extend this one backwards here, they all hit at a point. That point they hit at is our image. Okay? That's what happens when you use your lens as a simple magnifier. Notice that it's still upright, and here's the object. The image is bigger than the object. So we've magnified it. We've made it 2 to 3 times bigger, depending on the focal length of your lens and that kind of stuff. So that varies depending on the kind of lens you have. But that's the idea, is you magnify the object. Now the truth is that image is never on this side of the lens. It's on the back side of the lens. You can't ever see it. You can't put a piece of paper here and project it. That's what you call a virtual image, but you can see it. It appears to our eyes because the light rays seem to be coming from that point. They don't actually go through that point. They just seem to be coming from that point. All right, that's case 2. So how do you build a simple telescope? You just put case 1 and case 2 together. And that's what Hans Lippershey figured out and Galileo figured out, was it's not hard to build a telescope. You just got to get the right lenses in the right place. All right, so this is going to be what we call a simple refracting telescope. Refracting means it uses lenses. Okay? All right. So what I have is I have an axis here. And I have a lens. This is my first lens. Center lens. We have our focal point out here, some distance. It can be arbitrary, but it has to be the same on both sides. It has to be the same on both sides. Okay? So what do? I want to look at some objects. Extend this further. Make sure I don't go off the video. Here's my object right here. So this is what I'm going to start with. Here's my original object. Now we're going to do the exact same thing we did in case 1. We have a light ray. It's going to go through the focal point. It's going to come out parallel. We have one that's going to go parallel and go through the focal point. And then we're going to have one, I should be doing different colors here, that goes right through the center and just keeps going straight like that. Okay, so this is just case 1 all over again. I created an image right here. So this is the image from the first telescope, from the first lens. And we have a name. We have to name these lenses. So since this lens is closest to the object, we call this the objective lens. Okay. Then I'm going to put another lens right here. I'm going to put another lens right here so that oh boy, that's terrible. Work on the center of my lens here. Okay? So that the image, this image, is inside the focal point of this lens. So I'm going to put my focal point out here. This is the focal point of lens 2. This is lens 1, we'll call it, or the objective lens. And then I'm going to do the same thing on the opposite side. Extend my axis here. And now I'm going to take this first image, which is a real image, and I'm going to figure out where the image of that is with the second one. So from here, from this arrow, now this is my object for the second lens, I go parallel. I go through, this is the focal point, 2. I go through focal point 2. I got one through coming from focal point 2. I got to extend my lens out here because it went a long way. And then it comes out parallel. Okay. Then I got one that goes right through the center of the lens and just keeps going in a straight line. So essentially I've done what I did before. Now it's flipped upside down, but here's my object for this lens is this one right here. And I've just drawn 3 rays from the head of that arrow. The same rays that we've done every single time. parallel through the focal point, from the focal point on this side, out parallel, and then one through the center. And then, remember, this is case 2, so I have to actually extend them backwards to where our eye would see them to come together. If I extend that one backwards, and this one backwards right here, and this one backwards right here, they all meet right here. I'm going to draw this really big, because it is. This, right here, is the final image. And you see, we've taken an object and we magnified it significantly. We made it significantly bigger than it was originally just by putting 2 lenses in the right configuration. And the name for this lens up here is called the eyepiece. And that's what Galileo did with his telescope. Now, he actually used a negative lens here. You can do that too. There's ways to get around it. The thing about using a negative lens is that it doesn't flip it upside down, which is kind of nice. Or you can use another lens that flips it back over again. Or you can use prisms, which is what binoculars do. For astronomers, we don't care that it's upside down, because the star upside down is still a star, so we don't really care about that. Here is a simple refracting telescope. And how it works is, sorry, I got to grab a couple pieces here. As you see down here, that is the lens. This is the objective lens you see at the end inside the telescope. And this is the eyepiece right here, which is just another lens. And you put these together here, and you look through this, and you have a telescope.